Administration, as well as Professor of Information and History at the University of Michigan. Professor visiting professorships on 4 continents, and more recently, he's been appointed as a lead author for the 6th assessment report of the IPCC. So he is the first social scientist to serve as a lead author in Working Group 1, which assesses the physical science of climate change. He holds a PhD in History of Consciousness from UC Santa Cruz, Donna Haraway's program, for those of you in science studies. He is well known for his studies of the history of computing and cybernetics, but let me focus here on his contributions to interpreting the character of our knowledge of climate change. So if the climate crisis posed an existential problem for the discipline of science studies, caught as it was between unmasking the power of science and defending climate scientists from the manufacturers of doubt, then Professor Edwards showed us a way out. In his justly celebrated 2010 book, A Vast Machine, he demonstrated how climate science is indeed socially constructed, but also how that process of construction makes the science trustworthy. The book has been showered with prizes, including the Computer Museum History Prize from the Society for the History of Technology, the Louis J. Batten Award from the American Meteorological Society, and it was named a Book of the Year by The Economist magazine. And Professor Edwards' attention to the socio-technical infrastructures that undergird global sciences like climate science has launched a new subfield in the discipline of STS, infrastructure studies, to which his talk today is one of his latest contributions. His title is Time and Risk in Climate Knowledge, an Infrastructure Perspective. Please join me in welcoming Paul Edwards.
Debbie, thanks so much for that very generous introduction. I should point out that I am one of the first social scientists in Working Group 1, not the only, but one of very few. Before I get started here, I think it's important to take a look at this cartoon because it's going to come up again, and especially this little piece down here. So maybe we can go back 50 years and put a price on carbon. No, we better hurry. No, that's the great thing about this technology. So some of what I'm going to do today is kind of for fun and just interesting about the history of time and its relationship to weather knowledge and weather infrastructure and climate science. Some of it is very serious and very urgent. So here's what I'm going to do. We'll talk a little bit about the early relationship between the infrastructures of time, clocks and standard time, and weather knowledge. Then we'll talk about the long now of Stuart Brand and his colleagues and about infrastructure as a commitment in time. Then we'll talk some about the temporality of climate knowledge, the span over which we have learned what we've learned. I'll do a brief zoom through the history of climate, and then we'll talk about some climate risks for the future and their relationship to the temporality of infrastructure. So let's start with weather and time. So this is a building in Charing Cross, London, in 1852. And I don't know how well you can see it, but there are some interesting things in this image. One is that this is the office of the Electric Telegraph Company. And outside the office, well, on top of the office is this weather vane, a thing which you will still see on lots of old buildings, but most people never even notice anymore, was mainly there to show the direction of the wind. Outside is a public clock. A public clock. Now, why does that matter? And on the top of it is a time ball. So this particular building received a time signal from the Greenwich Observatory, and like many, many other buildings of its day, it had this time ball on the top. The ball would be raised just before noon to the top of that mast, and then on the moment of noon, it would drop so that you could set your clock very exactly to the time given by the Greenwich Observatory. The public clock outside is for the rest of the time when people are setting their clocks and watches by other means. Why does this matter? Well, I love this image. This is time in Dresden, Germany, and then the times of all other cities all over Europe at the same moment. And you see that they're not set off by 1 hour exactly, as they always are today, but by some number of minutes. And that's because time in this period, in the 1850s, and for many centuries before, was always solar time. So noon is the exact moment when the sun is directly above you. You typically, if that's going to be measured, that was done at an astronomical observatory, which had an instrument for detecting the transit of the sun and figuring that moment precisely. So all these clocks are set to the solar time at their location, and that's just what time was in the distant past, distant for us. Then you get the telegraph. And the telegraph was what was used in this, the electric telegraph company to send the time signal. It's also what was used to make early weather maps like this. This is 1872, the U.S. Signal Service. They are getting data from a number of points around the country, not a lot of them. There are just a few places like here where you can see a weather station on the map. And then they use that simultaneous collection of weather reports to draw a map of pressure and temperature around the country. Here is the U.S. Weather Service in 1880. And part of what you see here is these are all telegraph lines going out of the Weather Service building and into it so that it can receive these signals and make maps and then send them back out. And of course, the telegraph was the internet of its time. The British telegraph network, already in 1890, reached all the continents except Antarctica, and didn't go into the interiors of South America or Africa, but it did cover a great deal of territory, and there were many other telegraph networks as well. So it was really a globe-spanning system of communication. So in the 1870s and 1880s, weather people began to get very interested in this question of time. And one of the events that occurred was an attempt to observe the aurora along the northern boundary of the United States and up into Canada, and to take sort of an image, in a sense, by having people report what they saw in an aurora all at the same time. But the same time then meant solar time. And so the people who tried this found that it just didn't work because they couldn't really, auroras happen very quickly, and they couldn't correlate all the reports for the same time because there was just too much uncertainty about what time they were actually using. So the head of the Weather Service at that time, Cleveland Abb, put together this thing called the Bulletin of International Observations Taken Simultaneously, starting in 1875. So he figured a way to use simultaneous time as opposed to solar synchronous time. And it published for about 10 years. That man was also one of the people behind the establishment of railroad time in the United States. This had already been done in Britain with Greenwich Standard Time, but in the United States, this didn't happen until 1883. And the interesting sequel to this is that Standard Time took a very, very long time to establish. It was about 50 years before most countries had adopted Standard Time, and the last country to adopt Standard Time was Nepal in 1986. So here's what people thought about that kind of time in the day. This was a kind of imposition on them of a standard from above, and it was not necessarily a good thing. Railroad time will now dominate. The sun will have to rise and set by railroad time. People will marry by railroad time, preach by railroad time, open and close by railroad time. So, mocking this new idea, which of course is the world that we live in now. So the time balls were an important feature of this system in the United States. So observatories at the time observed mostly astronomical phenomena, the sun, moon, stars, planets, etc. They also set the time, and they also became the first weather stations. So they became observers not only of the astronomical phenomena I just mentioned, but also of meteors, hydrometeors. That's the origin of the word meteorology. Things that fall from the sky. They used their system to send time signals to clocks all over the country, and some of those places had time balls of their own, and those were used for local clock setting. So this is 1905 when this article was published. This did not, the existence of simultaneous time did not end an argument in meteorology about whether that was the right kind of time to use. And there's an interesting argument in favor of solar time for climatology, which is that the sun, of course, is the thing that drives the whole climate system. And so its apparent motion in the sky is also what should be used, Napier-Shaw would say, to analyze weather phenomena for climatological purposes. So standard time became established, but then we also got daylight savings time, known as summertime in the UK. And here too, like as with the observation of the aurora, an enormous confusion among observers due to the imposition of summertime, which not everyone followed, and could not be precisely attributed to one point or another of observations because it just wasn't known which time they had used to make their observations for this period of a few months. So here's what things look like today, and I think it's fascinating to reflect on this map. So the white zones here are the places where your local time is pretty much the same as solar time. But most of us are either ahead or behind solar time in one way or another. And I used to live in Ann Arbor in Michigan, and there's a very western edge of the eastern time zone of the United States. And I loved it because it meant that we didn't have the deep darkness that you get in Connecticut and Boston and places that are even further out to the east. At the end of the day, when we're having daylight savings time. But you see China, the time zone is actually over here. It has an 8-hour span that country covers, and the people on the far western edge of it are way, way behind the actual solar time at their location. Okay, let's talk about the long now. I mean, you may not have noticed this, but I'm using a different date format on these slides than the one most people use. And that idea comes from this interesting concept of the long now that Stuart Brand put out 20 years ago in a book and then became a project for a clock. So this is Brand's idea of what the long now means. So when people say now, they typically mean sometime around today or yesterday or tomorrow. I lived in South Africa for a while, and there's a very complicated system of time which involves present time, now, right now, now, and just now. These all refer to slightly different periods, but none of them actually means now. They all mean maybe later or maybe yesterday. So Brand is proposing, the origins of our civilization happened about 10,000 years ago with the dawn of agriculture. So we're 10,000 years into this period, and he's saying, let's think about time in terms of not the next generation or the next 7 generations, but the next 10,000 years. And so they began to design a clock that would actually run on its own without intervention or maintenance for the next 10,000 years. So they conceived this in 1986. They've been working on it ever since, and it is now actually being built inside a mountain in Nevada. It has a very complicated gearing mechanism. It's enormous. I mean, it's a gigantic silo in this mountain that they built for it. And in principle, it will ring chimes at the turn of every century for the next 10,000 years. And when you read this clock, you have a system like this. I mean, this will be a very long time in the future. How does all this relate to infrastructure? So when I talk about infrastructure, I mean, there are a lot of things, that's a very slippery word. I happen to edit a book series called Infrastructures for MIT Press, and we take all kinds of things as infrastructures. But in this case, I'm going to talk mainly about hard physical infrastructure. So things like canals and railroads, telegraphs, roads, airways, oil pipelines, the stuff we build to make our societies work. And an interesting thing about these types of structures are that they tend to last longer than most people. Right, so roadways, many of them have been where they are for thousands of years, just built on top of previous roads. Not so much in this part of the world, but in parts that are older. Same thing with railroads. You know, those tracks were laid in the 19th century. A lot of those rail beds have been there the whole time. They may have been maintained and replaced, but it's still basically the same system. And one item that's really interesting to me is that the lines of the telegraph followed the railroad because the rail beds were already there and the railroads needed the telegraph for their communication system over long distance. But not only did the telegraph follow that line, so did the internet. So this is what I'm talking about, and part of this slide is one of many we could show that pictures the kind of building period, how long it takes to go from starting up a new infrastructure to finishing it in the sense of, you know, people stop building a lot and they slow down. So in each of these cases, you see a period that's somewhere between 30 and 100 years. Often it's around 50 years from the beginning to the build-out phase. So that's a good part of a human lifespan. If we look at energy infrastructures, so here this graph starts in 1830 and runs through to about 2010. And what we see is that, you know, of course, before 1830, almost all the energy people used was wood and biomass of other types, dung and stuff like that. Then coal comes in, and coal gets very big, goes up to about 50% in around the time of World War I, and then begins to drop as oil comes in and begins to take over some of that. And then finally, in the 1950s, you begin to get a lot of natural gas. And then down at the very bottom, we have nuclear power and and hydropower. So small portions of the total amount of energy that people use, but still significant. Now, if you think about the infrastructures that are built to supply that energy, just looking at fossil fuels. So I heard this in a talk by John Holdren. I thought it was just a fascinating concept. These things don't last forever, so they are always being replaced, you know, pieces of them. You've got to fix parts of it. The oil tanker has a certain lifetime before it has to be broken up and recycled, and the pipelines and everything else. And the total cost of that system is about $10 trillion. So if we were going to start building the fossil fuel infrastructure today, that's what it would cost to make it again. That's about half of the United States GDP. So it's a very large number. It's also not an astronomical number. If we start to think about infrastructure and time, one of the things we see is that when we build stuff, we commit to it. So we don't just build the thing, like the highway system here. We're also building a system that requires a steady supply of energy. We become committed to modes of transport, like cars. We become committed to maintaining it, and there are many jobs in infrastructure that are essentially maintenance. You yourself maintain some of it, your driveway, for example, your storm drain. And those things in turn commit us to lifestyles and habits that become very hard to break. There's a path dependence effect. Now, about 9 years ago, in 2010, Ken Caldera and his colleagues did this really interesting study where they posed this question. What would happen if we just stopped building any new infrastructure and let what's already there live out its useful life? So, as if we could just quit today on fossil fuels. And the finding was fascinating because what they said was, if we could do that, that all by itself would keep the planet below the 2 degrees centigrade target. So a lot of the emissions that we're looking at in the future come from stuff that hasn't even been built yet, but that we are continuing to build because we are already committed to those systems of energy provision. So I'm now going to show you a short video of the atmosphere of the planet and its temperature since about 1880. And I want you to see this video as the effect of infrastructure. So what's going on during this period is the consumption of coal and the consumption of oil and natural gas are rising and rising and rising. And the temperature changes that you see, especially after the 1970s, but really back into the 30s and 40s, are the effect of that infrastructure. So part of what happens with us is that we can't see this directly. We can only see it in data. We can't see it in, you don't see the carbon dioxide coming out of your car, for example. What about climate knowledge itself? So one of the concepts I like to talk about is that we have another kind of infrastructure. There's the hard physical infrastructure. There are also infrastructures for creating knowledge. It needs to be generated. We need to collect data. We need to analyze it. We need to process it into forms that people can use and then put it out. So we do that with people and equipment and institutions. When I call something a knowledge infrastructure, I'm talking about something that is reliable and widely accepted. So weather forecasts are a great example of that. You know that it's not going to be precise. It might be wrong by a little bit, but you don't expect it to be wrong by a lot. And if it says it's going to rain or going to snow, you're going to prepare yourself appropriately for that day. You don't expect, temperature swings of 80 degrees in the course of one day, even though that happens once in a while. There are lots of other things like this. So the national census is one. The CDC gives us projections of what's going to happen with flu or Ebola or measles. And then we have weather forecasting. We have also labor statistics. They come out every month. That's a data collection process, an analysis process, and so on. Most people have no interest whatsoever in how that stuff is created. They just use the output, right? So it's infrastructural. In terms of weather knowledge, this goes back in the scientific knowledge about weather, goes back a long way, but the infrastructure part of it really begins getting built in the middle of the 19th century with these observatories establishing weather observation as part of their mission. Weather stations stand for a pretty large area. And today, we have this incredibly complicated machine that gives us this information about the weather every day. We have sensors in the air and in space, on land, at sea, underwater, all over the world. It was planned in the early 1960s. It was actually operating long before that in other forms. And then these sensors send their information to giant computer systems in a few places, which process the data and create weather forecasts, which they then send on to the National Weather Services, who add some more processing and create local forecasts and send them out to you. There too, you probably pay no attention to the process of production of any of that. You just use the output. Now, throughout this process, there have been lots of conflicts. it was not a steady, smooth, even progression. There were conflicts over standards and over what kind of information technology to use. They began to build it long before the internet, and they faced all the same problems of addressing and multiple overuse of a channel by sending the same broadcast many times, many other things. There are weather stations that have been in the same place, but have passed through a whole series of different political structures during this time, and each time that happens, some things like standards can change, because the whole system is a collection of national weather services that are independent and set their own standards. There's this World Meteorological Organization that tries to keep them focused on doing the same thing, but it doesn't always work. So the skill of this system is really a remarkable thing. So here's through 2010. This is the forecast for 500 millibars. So this is high in the atmosphere, but it's what's known as a steering level. So it's the part of the atmosphere that kind of moves weather around, and what we experience on the ground is not the same, but this is in a lot of ways the most useful part of the forecast. And you see that back here in 1955, at the very beginning of the computer era, when they first started using computer models, forecast skill was pretty bad. They're getting about 25%. And these are new computers coming in, each with a higher, allowing higher resolution, more processes to be modeled. And as that goes on, the skill level gets better and better, so that the 72-hour forecast is as good today as the 36-hour forecast was 15 years ago. So in terms of, I could spend a long time on climate science itself, but I won't, because you probably all know this. This is a really interesting thing that's people have just been doing this in the last couple of years. So, the famous Jim Hanson statement before Congress, using his model from 1988, he made, so they have the observations, which are the blue, the dark blue and the light blue lines, and then 3 scenarios. So the hindcast is based on data, right? And this is when he makes the forecast. And then he's got 3 scenarios for what might happen in the future. And if you just look at the scenarios, you see that he didn't really, these scenarios seem to go a lot higher than what actually happened. But of course, the scenarios are just predictions of what might happen in the future. They're not data about what did happen. And if we change this graph and use, instead of the scenarios, use the actual radiative forcing, so all the data we have about what has happened since then in terms of emissions, it looks different. So here we've got the black line observations going up to here, and you see that it's actually tracking quite well with the scenarios if we revise them in this way. So, the point I always make about this is this system of knowledge is very old, it's robust, and the weather infrastructure part is a piece that we tend to trust without a lot of thought. The climate part is one where we're still getting nasty debates about it. And yet, the modeling systems that are used to do both of these things are actually the same models. And so the most important climate modeling centers have moved from having a bunch of climate models and then a weather forecast model, they're kind of separate enterprises, to having what they now call the unified model. So it's the same model that is being used in a different mode to project climate. Resolution has to be lower. Some of the things that aren't included in weather models have to be included because they don't matter for weather, but they do matter for climate. So we're literally, the same system is now being used for these, our climate projections. Okay, I promised you a zoom lens. Here we go. 800,000 years, proxy measures. The CO2 concentration actually is not a proxy measure. That's a direct measurement of atmosphere from the distant past trapped in ice cores. The temperature is read by a proxy of an oxygen isotope that's contained in that same atmosphere, so it's not a direct reading of temperature. Of course, we can't get that, but we can get a very close proxy for it. And of course, this is only one point. So this is Antarctica. It's not the most important place in terms of our lives, but it's still an interesting thing. So we are actually, a piece to add to this is that human beings as a species emerge in their genetically modern form about 200,000 years ago during this period. So what this tells you is that we're here at a much higher level, and our temperature has also, this is Antarctica, but our temperature has also risen above the last 1,000 years and is promising to go up at least another degree or two before we get control of it. And it means that people as physical bodies evolved in climates that were always colder than the one we live in now. We are built for a colder world. That's where our carbon dioxide concentration is today. Now, if we zoom in from this to 100,000 years and look at it as a species history, we see the same thing. So we have the oxygen proxy for temperature going back about 100,000 years. People leave Africa, they go to Australia and South Asia and Europe. And up here is where the temperature stabilizes in the Holocene and remains remarkably stable for the last 12,000 years. And that corresponds exactly with the birth of agriculture. If we zoom in on the 10,000 year time scale, we see that there have been some periods during the Holocene when it was warmer than today. So the Holocene mean, the whole period of the last 12,000 years is here. The mean of the last century, starting from going backward from 2016, is here. The mean of the last 10 years from 2016 is up there, and 2016, the warmest year on record, is way up there. So we are getting way outside the Holocene mean. 18 of the 20 warmest years ever recorded have happened in the last 20 years. If we zoom in even further, we see the famous medieval warm period, often an object of debate among the deniers, the Little Ice Age. There's a recent paper, which I don't think I believe, but it's sort of worth thinking about, that points out that this period, the Little Ice Age, corresponds to the period when Westerners colonized the Americas and wiped out vast numbers of indigenous people, leaving the land that they had cultivated or burned for hunting or agriculture to reforest. So the concept is that there's about a 5 part per million drop in the CO2 level during that period that can be attributed to people, or rather to the absence of people because of the mass extinction they experienced. And then the last 100 years, we see the steady creep of temperature up. There's a period here where it flattens out, and the interesting part of this is that that's likely linked to the increase in aerosols from coal burning all over the world. And what we see here, some of it is unmasking of that as emissions control technologies come in. All right, the last thing I'll talk about is climate risk and infrastructure time. So how are the long time spans of the infrastructures we build going to be related to the risks we face as the climate changes? And there's a lot to say about this. I could go on and on about it, but I'm just going to talk about a couple of things. One is the 2003 European heat wave. So this was a period of about 3 weeks when the temperature got very high in Central Europe, in France especially, and stayed that way not only during the day but also at night. And that's rare in Central Europe. Usually the temperature drops back down at night and rises again, even if it's very hot during the day. So 30,000 people died during that heat wave, a lot of them in Paris and in southern France. There were a lot of forest fires and crop damage, 9.3 billion euros in economic losses. But the deaths are interesting because they're related to the infrastructure of housing in that part of the world. So here is a typical house in southern France that was built probably within the, between 100 and 300 years ago. They're made of stone, they have tile roofs, and they're built to survive a hot climate because the stone is thick, has a lot of thermal inertia, and if the temperature cools down at night, it kind of keeps the building moderate even during the middle of the day. During that heat wave, it didn't cool down at night, so that system of cooling no longer worked. A lot of people died in Paris for the same reason. The buildings there are also made of stone, and they work pretty well for cooling as long as the temperature varies during the day, but not if there's a long heat wave. So there was a heat wave in the Middle East in 2015 that's really an amazing phenomenon. So, 50 degrees centigrade is 122 degrees Fahrenheit. And, you see some high temperatures on this list, but take a look at this. This is Kuwait and Iraq. And the temperature there was about 52 degrees Fahrenheit for several days. We've got in fact, there was another heat wave in this place in 2017 where the temperature in Kuwait went to 54 degrees, the highest temperature that has ever been recorded as far as we know. There's a Death Valley record, but it's higher, but it's probably false. Now, if we look at what's going to happen, and just look at one place, a really important place with a lot of people, India, the projections for the high-end scenario, the sort of business-as-usual scenario, put the temperatures on so now we're using a wet bulb temperature, which is a good way to measure what the temperature is like in a humid place. So this is a place where there's very high humidity, often 95%. And we see that in this part of India, we're going to be pushing 35 degrees, which is lethal to human beings if they stay outside in it for more than 4 or 5 hours. Now, the people who live in that area mostly are involved in agriculture. They work outside. Their shelters are not air conditioned. So there is no infrastructure there that can protect them from those temperatures. In terms of the knowledge infrastructures we have, there's this phenomenon that we learn more and more as we go on, but that temporality of learning affects what we do, and it has been, in a lot of ways, too slow. If we knew 30 years ago exactly what I'm telling you today, things might have happened a bit differently. And here's just one example. So in 2007, the National Defense Authorization Act directed the Defense Department to use the mid-range of the IPCC sea level rise forecast for planning around naval bases. So the 2007 forecast was here, somewhere, with the center line on about a half a meter. But as soon as that report was published and the NDAA the plan had been made, new estimates came out that put this much higher. So now the estimates by 2100 are much more in the range of a meter on a business as usual scenario, or even higher. So another infrastructure effect, one closer to home, and something that can affect people here in this state as well, and especially right here on the coast where we are, is that we have already seen in the last 10 years, this is an analysis that goes back to about 2005, and just, it's a 10-year analysis of all the properties that lost value due to sea level rise and flooding, and the estimate's about $7.5 billion, 616,000 homes. One of my climate science colleagues inherited a house on the coast of North Carolina in 1982. And he didn't use it a lot himself. He mostly rented it out and didn't pay a lot of attention to it. He went back this year to sell that house and discovered that the entire basement and substructure had been ruined by water intrusion. So this is a story that's going to get repeated over and over again very slowly as it affects, each house and place differently over time. So another thing about the temporality of risk, and the hardest one to really face, is that we have already built in a lot of inertia that we won't be able to stop, no matter what we do. So even if we stopped emitting all greenhouse gases tomorrow, the methane concentration would come back down. The nitrous oxide concentration would take several centuries, but carbon dioxide would never come back to its pre-industrial level on any time scale that matters to us. So I'm going to stop with this slide and just say the challenges of infrastructure that we face are truly enormous. If we think about those 50-year time periods for building things, the 30 to 50-year replacement time for any infrastructure, the cost of it all, there's a lot of work to do. And this is from the 1.5 report that came out last fall, the IPCC report, on what could you do that would keep the planetary temperature down to 1.5 degrees. Now, the interesting thing about this graph is that this pathway is all aspirational. There is no reality to it at the moment. So the concept here is that if we peaked in 2030, 11 years from now, and then began to draw down carbon dioxide with technologies that pull carbon out of the atmosphere, then maybe by the end of the century, we would reach a place where we could be having net negative emissions and really, stabilize the climate that way. Now, what would that involve? I mean, we've got all the things that are really popular among the green movement, renewable energy, that's great, fabulous. But it would also involve nuclear power, because there's just not a way to get to that scale fast enough with renewables. We're starting from a tiny base, and even though they cost less and they're better in a lot of ways than the alternatives, the rate of increase is not high enough, can't be high enough to replace everything overnight. So maybe you can find ways to capture and store carbon. And there are the biological ways. There are planting trillions of trees. That would help. There's restoring the prairie. There's lots of other things like that that could pull some carbon down biologically and store it. But of course, we're already using a lot of that land, and figuring out a way to place that you can actually plant trees and other and grasses and other things is hard to do. So maybe you need to do it technologically, and there are operating power plants now, coal-fired power plants that can pull some of the carbon out of their emissions and store them underground. But those systems only work in a few places where the geology permits, and they're not that good, and they make the electricity very expensive because there's an energy cost for the capture and storage. So then maybe we need artificial trees and artificial photosynthesis and things that can literally just grab carbon and store it somehow. And this graph assumes that we will figure that out, but we don't know how to do it yet. Now, I hope we figure it out. I want more research on that, because maybe that will be an alternative in the future. So anyway, enormous infrastructure challenge, and closely related to the temporalities of risk and time. I'll stop there. Thanks. And Debbie asked me to take my own questions, which is fine. We've got a mic back here for anyone who wants to make a comment or ask a question. Fire away.
Hi, thank you so much for your talk. I was wondering if you could comment at all between the reported discrepancy in the European models of forecasting and the U.S. models of forecasting for weather.
So what's the question exactly?
Basically, if you had any insights into why there is a discrepancy between the European model, which is usually regarded as more accurate than the U.S. model.
I haven't tracked it closely in the last 10 years, so I couldn't tell you about what it's like today. That, the ECMWF, so the European Center for Medium Range Weather Forecasts, is known as the best forecast center in the world. You're right. It has engaged, since it started, in a routine of revising the model on a period of about every 6 to 9 months. So they take the model they have, they make improvements to it, they run the new model side by side with the old model, and they wait until they can see that it's actually doing a better job, and then they replace it. And the last time I looked at it, they were on cycle 50 or 51, something like that. So they've done many, many rounds of revision, and that's how you get better. It's all about incremental change. I'm not sure why the U.S. models don't perform as well. Can't really answer that. And the way a lot of the forecasting centers work now is that they don't actually make just one weather forecast. They make about 100, and they use the ensemble as a way of testing statistically for what's most likely. So sometimes you get a big peak in the middle, and that's what the forecast will be. But sometimes it's bimodal. You get two different forecasts that are sort of equally likely, and then they have to do some kind of intuition.
You had that one graph kind of early on that had sort of the time to build out of a bunch of different infrastructures, like Telegraph in the railroad.
Oh, yeah.
Sure. A lot of those are, it seems like building out a new technology, where what you're talking about here is reversing or swapping out a technology. Are there similar examples of those that maybe have a different shape of that curve, or are there reasons to believe that swapping out would be radically different?
Well, so maybe the best example of that is what happens to power grids when you put, a lot of renewables into them, and that's a worry in a lot of countries. If you have all renewables, then you don't have a source of base load for the times when there's no wind and no sun. So when you talk to power company people about this, they'll often say, well, we have to have nuclear, or we have to have gas or something to back up the energy system. So there's that aspect of it, and then there's the aspect of the ability to transmit that power. It's actually better used at the source because it's generated as DC and it has to be inverted to make AC power, and you lose a lot of power in transmission lines. So there are complexities like that, but I don't have a good sense of. Yeah. Yeah. Well, you can think about it in terms of electric car charging stations. We've got a vast network of gas stations. Those are, you can find those anywhere, but not electric power stations for cars. So you have to kind of substitute this whole new thing, and you could even do it in the same place, and you find gas stations now that have car charging stations at their location, but it's not an obvious overlap, and it has to be done by a different company and requires high power. The best ones, you'd want to be able to charge your car in 5 minutes like you can with like pumping gas, and that can be done, but it requires a really high voltage for the power system, and not something that a gas station attendant would know about. So there's all the kind of training and knowledge that goes into the system, as well as the substitution itself.
As someone who's thought about time a lot, I wonder if personally you can tell us anything about how you've come to understand not only the passage of time, but the change in which time's taking place. So I'm referring here to this concept that may be debunked by now, that our minds evolved over evolutionary time, but now we're trying to make decisions in much shorter periods of time. So I'm wondering if, since you've thought about all this and could present this all to us, have you been able to come up with any way of thinking differently about the recent now, the now, and the soon-to-be now? Whatever definition you want to put on those.
I wish I could say yes, but I don't think I have. I mean, a book that had a huge influence on me that actually everybody should read, and it doesn't take long, is Thinking Fast and Slow, the Daniel Kahneman's book about psychology, which essentially says we've got two systems in our minds. One is for making very quick choices. It's intuitive, it's based often on emotion, it's based on your past history. You tend to see things that confirm what you already believe rather than to change your mind every time. And that's very powerful. It's the way that people make decisions most of the time. And the slower system takes days, weeks, months, and involves thinking about data and really visiting facts. We can do it, but we're not very good at it. And as a society, we're now being pushed more and more into that very short decision-making frame by social media, where you see, instead of a long disquisition on something, you get a meme, and you look at it for 3 seconds and you decide whether or not to share it, whether or not you believe it, but you often don't actually go check whether the facts behind it are real. So there's that piece, and then the other issue is just our seeming inability as a civilization to think about long-term risk. We're always overwhelmed by the short-term risks, and I wish I had a solution for that, but I don't. The one thing I'll say that I never thought I'd hear myself saying this, but the Chinese government is really doing huge things on climate change, and it's able to do that because it's an authoritarian system. They have made a hard left turn in the last 10 years around coal-fired power, solar energy, and reforestation. And they have massive projects on that. They're really turning the whole society to that project. And they can do it because it's a command economy. We will not be able to do that. We have to somehow tax or vote or something, and those things are always contentious and they take way too long.
Hi, Paul. Thanks for the talk. So I wanted you to say a little bit more about your critique of this recent study about the Little Ice Age being related to the massive genocide of indigenous people in the Americas.
Well, it's really mainly intuition that it's, we're talking about 5 parts per million over about 270. So it's a very small fraction of the total amount of carbon dioxide. And I'm not sure I buy that that's enough to cause the temperature change that we saw. It's intuitive. It's not a deep critique, and I need to look at it more, see what other science comes out around it.
For building in resilience and adaptation. And what flashed through my mind when I read it was, 3 or 4 generations from now, are people really going to be congratulating themselves for these measures? I'm curious, what is your take when you see an op-ed like that, and in the context of coastal cities?
Yeah, I didn't see it, so I'm not quite sure. What did he say exactly? Just what have they done that they?
Well, they were praising some of the measures that Miami has been taking with bonds and monies that they are raising to build a seawall and, take all these other measures to prevent damage from rising waters.
Yeah. Well, speaking of new infrastructure, I mean, that's what is going to happen in a lot of places, seawalls and attempts to kind of shunt it aside. And if they're high enough, they'll probably work for a local area, but they're not a solution to the problem for most people. And my colleague Chris Field at Stanford, who is another IPCC person, been involved in it since the beginning, he talks a lot now about managed retreat. How do we pull away from the coastlines? Where do people go? And is there a way of planning for that could actually produce some positive effects by deliberately designing communities and housing systems and transport and so on to make life better for people instead of just be refugees. But there too, it seems like a great idea, but how you execute that, especially in a democracy, is really hard to imagine. Yeah, I mean, another piece of this that I learned about this recently, and I hope I understand it right because I've only read one article about it, but it was pretty detailed, is the insurance industry. So, let's see, how can I say this very briefly? The insurance industry uses models to predict risk. And in this country, it's regulated, so politicians control whether prices can rise or not. And there was, in the last 10 or 15 years, an attempt to bring climate change into the models they use to project risk, and it has been rejected. So that they have the risk models, but they're all based on the past, and they can't actually use climate change projections to set insurance rates. If they could, you would rapidly see insurance rates rise in coastal areas, in fire-prone areas, all kinds of things, and that would help, all by itself would have an adjustment effect. Great pleasure. Thank you. Hey.
Thank you for the talk.
My pleasure.
Can I just give you a little observation?
Yeah,
about
please.
that thing you said about China?
Yeah.
So I think that culturally speaking, Chinese have a very long view within,
Yeah, that's true.
and Europeans
Yeah.
more than Americans, but
Yeah.
less than Chinese.
Yeah.
And so what you think about the Chinese might be more related to their culture
Yeah.
than to their former government.
Yeah, that's true.
I'm not saying
Well,
that it doesn't matter.
I'm
saying that just, that
I
only
agree with you. Yeah.
that,
I just heard a talk about this by a Chinese guy and one of the things he said is that this policy they have now, that any policy that's going to make a big effect in the government there has to be grounded in both Marxism and in ancient